Suppose someone hands you a matrix and asks for its inverse. You could set up a system of equations for each column of the inverse and solve them one by one. For example, you'd form the augmented matrix A with E1, then separately form A with E2 and solve each system. But every system shares the same coefficient matrix A, meaning you repeat the same elimination steps over and over. There's a far better way. Instead of solving these systems separately, append the entire identity matrix to A, forming the single augmented matrix A with I. Now a single procedure called Gauss-Jordan Elimination finds the entire inverse in one pass. The same row operations are applied just once and both systems are solved simultaneously. Here's the setup. We want A inverse, the matrix where A times A inverse equals the identity matrix I. Now let's think about what this equation means column by column. Well, the first column of A inverse, call it x1, satisfies A times x1 equals E1, the first standard basis vector, which is 1 on top and 0 on the bottom. On the second column, x2 satisfies A times x2 equals E2, which is 0 on top and 1 on the bottom. Each of these is a separate linear system, but notice that both systems share the same coefficient, matrix A. That's the key insight. Because A appears in both systems, we can solve them simultaneously using one augmented matrix, a single matrix formed by appending the right-hand sides as extra columns to the right of A. That gives us the augmented matrix A augmented with E1 and E2, which is simply A augmented with the identity matrix I, same A, different right-hand sides, so we batch them into one augmented matrix. Let's see this with a concrete example. Take A equals the following 2 by 2 matrix. Row 1 is 1, 3, row 2 is 2, 7. Now we form the augmented matrix by writing A on the left and the 2 by 2 identity matrix on the right, separated by a vertical line. So the augmented matrix looks like this. Row 1 is 1, 3, vertical line, 1, 0. Row 2 is 2, 7, vertical line, 0, 1. The left half, shaded in blue, is what we will transform into the identity matrix through row operations. And the right half, shaded in green, starts as the identity and acts as a recorder. Right? Like every row operation we perform on the left side, we also perform on the right side. When we finish reducing the left half to the identity, the right half will hold A inverse. Now, the Gauss phase, forward elimination. A pivot is the leading non-zero entry in a row during elimination. Our first pivot is 1. In row 1, column 1. Row 2 starts with 2, so we perform the operation R2 gets R2 minus 2 times R1. Let's walk through each entry one at a time. Row 2, column 1, 2 minus 2 times 1 equals 0. Column 2, 7 minus 2 times 3 equals 1. Now the right side, column 3, 0 minus 2 times 1 equals negative 2. Column 4, 1 minus 2 times 0 equals 1. So our matrix is now 1, 3, 1, 0 in the first row, and 0, 1, negative 2, 1 in the second row. Notice the left half is now upper triangular, and this is where Gauss would stop, but Jordan keeps going. Now the Jordan phase, backward elimination. The goal is to create zeros above each pivot. The second pivot sits in row 2, column 2, and its value is 1. Row 1, column 2 has a 3, so that's our target to eliminate. We perform the operation. R1 gets R1 minus 3 times R2. Let's compute each new entry one at a time. Row 1, column 1, 1 minus 3 times 0 equals 1. Column 2, 3 minus 3 times 1 equals 0. Now the right side, column 3, 1 minus 3 times negative 2 equals 1 plus 6, which is 7. Column 4, 0 minus 3 times 1 equals negative 3. The left half of our augmented matrix is now the identity matrix, so the Jordan phase is complete. The right half reads 7, negative 3 in row 1, and the negative 2, 1 in row 2. That right half is A inverse. Quick verification, let's multiply A times A inverse to confirm our result. We take A, which is the matrix 1, 3, 2, 7, and then multiply it by A inverse, which is 7, -3, -2, 1. We'll compute each entry of the resulting 2 by 2 matrix 1 at a time. First row, first column, 1 times 7 plus 3 times negative, 2 equals 7 minus 6, which equals 1. First row, second column, 1 times -3 plus 3 times 1 equals -3 plus 3, which equals 0. Second row, first column, 2 times 7 plus 7 times -2 equals 14 minus 14, which equals 0. Second row, second column, 2 times -3 plus 7 times 1 equals -6 plus 7, which equals 1. The product is the 2 by 2 identity matrix with 1s on the diagonal and 0s elsewhere. Our inverse is confirmed. We've seen the method work. Now let's understand why. Each row operation is equivalent to left multiplying by an elementary matrix, a special matrix that performs one specific row operation when it multiplies another matrix. Our first operation, R2 minus 2R1, corresponds to E1, the matrix with rows 1, 0, and -2, 1. Our second operation, R1 minus 3R2, corresponds to E2, the matrix with rows 1, -3, and 0, 1. When we apply both in sequence, E2 times E1 times A equals the identity. This means E2 times E1 must equal A inverse. Now, here's the key insight about the right half. The right side of our augmented matrix started as the identity, and it received those exact same row operations, so the right side became E2 times E1 times I, which is just E2 times E1, which equals A inverse, the identity recorded every step we performed. Let's confirm by multiplying E2 times E1 directly. For the top left entry, 1 times 1 plus -3 times -2 equals 1 plus 6, which is 7. Top right, 1 times 0 plus -3 times 1 equals -3. Bottom left, 0 times 1 plus 1 times -2 equals -2. Bottom right, 0 times 0 plus 1 times 1 equals 1. The product is 7, -3, -2, 1, matching our answer perfectly. Let's now discuss 3 common pitfalls, but first let's clearly distinguish the 2 phases of the method. The Gauss phase, also called forward elimination, has the goal of creating zeros below each pivot. The result is an upper triangular left half of the augmented matrix. This is sufficient for solving a single system via back substitution, but it is not sufficient for reading off the inverse. The Jordan phase, so also called backward elimination, has the goal of creating zeros above each pivot. The result is the identity matrix on the left half. Only then is the right half the inverse, which you can read off directly. Now here are 3 pitfalls to watch out for. Pitfall number 1, you cannot skip the identity. Without augmenting the identity matrix on the right half, you have no recorder. You will reach the identity on the left with no trace of how you got there, and therefore no inverse. Pitfall number 2, a 0 pivot does not mean failure. If you encounter a 0 in the pivot position, simply swap rows. That is a perfectly valid row operation. The method only truly fails when no non-zero entry exists anywhere below the pivot position, which means A is singular and has no inverse. Pitfall number 3, do not stop at upper triangular. The Gauss phase alone will not give you the identity on the left, so the right half is not the inverse yet. The Jordan phase, the backward elimination, is essential to complete the process. Gauss-Jordan elimination is the algorithmic backbone behind matrix inversion. Every time you solve AX equals B by computing A inverse times B, every time you change coordinates in computer graphics or fit a linear regression, matrix inversion is there working behind the scenes. For large-scale numerical work, Methods like LU decomposition are preferred for efficiency, but the conceptual foundation is exactly the same. Factor the work into elementary row operation steps. So let's summarize the entire method in 3 clean steps. Step 1, append the identity. Form the augmented matrix with A on the left and the identity matrix I on the right. Step 2, row reduce the left half to the identity matrix, applying both forward elimination and backward elimination. Step 3, read off A inverse from the right half of the augmented matrix. That's it. These 3 steps connect to a wide range of applications. Solving AX equals B, computer graphics transformations, and linear regression all rely on matrix inversion via Gauss-Jordan. The final takeaway to remember: append, reduce, read.